And so generally we see the graph is going up. And so that would be called a positive correlation, you could say. That might have been something you said about this. Or you could say as the number of resumes increases, the number of interviews also increases. Which kind of makes sense. If you let employers know who you are and that you're interested in a job, you are more likely to get an interview. And so we would say that that's a positive correlation. It doesn't make a perfect line. It's not a super tight correlation, but it is, we do see an increasing positive correlation. So the number 8 says, based on the scatter plot, if a person sent out 20 resumes, about how many interviews do you think the person will receive? And so to solve this, we would go to 20 resumes and we would look above it and see generally where the points are around there. And so this is not a right or wrong answer. If it was multiple choice, there would be, a range that you have to be within, but you might have said 2 to 3. You might have said 3, okay? But somewhere around there should be your answer. Okay. All right, those are the only ones I was going to go over specifically. Anybody do any of these others that they have a question on page 23? Or a question on 5 through 8 that we just went over? Okay. Well, again, I would encourage you to work through, you've got the mixed review on pages 23, 24, and then starting what's called Unit 1 review starting at page 25. And so all of those problems would be good problems to practice. And remember, you get a lot of bang for your buck on this topic because this topic is on math, it's on social studies, and it's on science. And so you are literally studying for 3 tests when you do this packet and this review work. So it's good bang for your buck topic. All right, so we're actually going to leave this packet now, and we are going to move to, it's posted on Canvas. It's called Probability Packet, and I'll put the link in the chat, but you can also find it on Canvas. The mouse is misbehaving this morning. Okay, that's in the chat. And so we're going to move to a topic called probability. And again, this you would see this topic both for sure in math and science. I'm not sure you would see it in social studies. Julie, you got any thoughts on that? Julie may have stepped out. There she is. Can you think of any?
I've never seen probability on social studies, but definitely measures of center, but not science and math for probability as far as I've seen.
And we're going to actually cover a lesson that's specific to probability that occurs in science called Punnett squares. Not today. So we're going to start with, there's a topic about counting, how to count situations and figure out how many situations are possible in certain settings. And that kind of lays the foundation to be able to calculate some probability problems. Then we'll move into straight probability, and then we'll look at the science application, and we'll finish this unit before the holiday break. And so my hope is that the last class before the holiday break will either be review as a class, or if some of you are ready and want to take a GED practice test in math, that that would be a day in class we could use that for. So we basically only have 6 classes before the Christmas, for the holiday break. We've got 3 weeks. And so we're gonna put in this unit here. We'll do some review, maybe a practice test before we break for the holiday. So the first topic is more like a problem solving topic in the sense that we're going to eventually get to how to mathematically calculate these things that are in this first lesson. But it's also a good idea to think about how you could draw it out and map it out for a few reasons, because sometimes we get nervous on a test and we forget how to do it mathematically. And so this would be a strategy you could use when you've panicked and you can't remember how to calculate it mathematically. We can draw out things. And sometimes there's problems that just make sense to solve using a picture or a diagram that you create that may be more efficient even than the mathematics. And so this is more kind of like a little problem solving lesson. It's not super hard, but it gives you some creative license, I guess, to figure out the best way to solve the problem. And then we're going to go to how do you calculate it mathematically, the shortcut, basically. So counting strategies is about counting how many scenarios with a given situation. So if you look at the first example, a classic problem is this one, and that is the idea that you have 4 people or 4 books or 4 somethings, and you're wanting to see how many ways you can arrange those 4 books or 4 people. And so this problem setup is we're taking a photograph of 4 children, very conveniently named with the first letters of A, B, C, and D for us, Alan, Bianca, Callie, and Dennis. And they're going to stand in a line. And so the question is, how many different ways can the children line up? Okay. And so one way to do this is simply to start writing out all the ways that they can line up. And as long as you have a small number of kids, this is a practical way to solve the problem. As we start getting into 10 kids and 12 kids, we really need a better mathematical solution. But this is a good fallback position to think about how you would solve this problem. And so basically, they're going to approach the problem, and hopefully you will too, in an organized manner. They're going to say, well, let's just write all the orders of the kids where Alan, signified by the letter A, stands at the left-hand side of the line. Okay. So you can have A, B, C, D, or you can have A, B, D, C. And those are the only 2 choices where A, B are the first 2 kids. Okay, so then you can put A, C, and you've got 2 kids left, and they can be in one order or reverse order. And then finally, you can have A next to D. And again, the last 2 kids can be in one order or they can be reversed. Okay, and so we found there are these 4 ways that the kids can stand in a line with Alan on the left-hand side. Okay. So now you have to account for, well, what if Bianca B stands on the far left-hand side? And they've just done the same thing. You can have B paired with A and kids C, D, or D, C flipped, and so on. And so they're going about in an organized manner, making lists of how the kids can stand. Okay. And so then when you get done, you've exhausted all the possibilities because you've exhausted A standing first, you've exhausted B standing first, you've exhausted C standing first, and you've exhausted D standing first. There are no other ways. And so then you simply count up how many ways there are. There's 4 ways for each of the 4 kids. And so you could count them 1, 2, 3, 4, 5, 6, 7, or you can say 4 ways times 4 beginning kids is 4 times, where am I getting 6? 4 times 4 is 16, but where are we getting 24 here? What am I missing? 1, 2, 3, 4. Oh, there's 6. Huh. Yeah, I can't count today. Apparently I should have counted them out 1 by 1. My goodness. There's 6 ways.
Clustered in groups of 2, it's hard to count them separately. I
So
was confused too.
just so you know, I'm not perfect at math either. I can't count to 6 today. So there are 6 ways for each of the 4 kids to stand in a line. And so you could count them all, or you can say 6 times 4 is how they get 24 possible ways and all. And you may say, well, that really stinks to write all those out. And again, we're going to go to finding a more efficient way in just a minute. But this is a good way that if you're on a test and you're like, I can't remember the math way, you can write it out. Once you get past about 4, it becomes very challenging to write them out because there just get to be so many. But you could actually see a problem which asks you how many ways are there to arrange 3 kids, and that wouldn't take you very long. Okay, so that's one way, just simply making a list. Another way you might tackle a problem like this would be a diagram like this. And the second example is another classic kind of problem in these this topic. Sometimes this is clothing. She wants to wear red, white, and blue for a holiday, and she's got, 2 pairs of sneakers. She has 3 shirts, and she has 3 pairs of shorts. How many outfits can we make? This one is a little different because it's not just how many outfits can we make, it's how many outfits can we make if she wants to wear one red item, 1 white item, and 1 blue item. A more classic problem of this would just be how many different outfits can you make from 2 sets of sneakers and 3 shirts and 3 shorts. Okay. And so you could do the same thing that we did up here, making this list, but you can also make this kind of tree diagram, which for some people makes a lot more sense in terms of organization. And so we've got our sneakers. She has a white pair and a blue pair. And let me highlight what we have here. So we've got our sneakers, blue and white. She's got 3 shirts and 3 pairs of shorts. And so if she pairs the white sneakers with the blue shirt, then her only choice for shorts is red because she wants to wear red, white, and blue. But if she pairs those white sneakers with the red top, then she'll wear the blue shorts because she wants to wear red, white, and blue. So she's not going to pair the white shirt with the white sneakers because then she won't have on red, white, and blue. And so then you only have the other choice of the blue sneakers. And again, you're only going to pair the blue sneakers with either the white shirt or the red shirt because we wouldn't want to wear the blue shirt because then she won't get red, white, and blue that she wants. And so they've made this diagram where you can see then how many choices she has. She'd have a lot more fashion choices if she didn't have the restriction that she wants to wear red, white, and blue. Okay. Then to count how many possible outfits there are, okay, we come over here to this side of the diagram. Because remember that white, blue, red is one option. And then white, red, blue is a second option. Blue, white, red is a third option. And then blue, red, and white is the fourth option. So you could either count the options here at the end to get 4, or you can follow the paths and count that there's 4 paths to her 4 outfits. And so she can only make 4 outfits if she restricts herself to wearing red, white, and blue. So an interesting question. Let's take some time, and down here at the bottom, let's take away that restriction. So she wants to know how many outfits can she make with 2 sneakers, 3 shirts, and 3 pairs of shorts. And so you can either, I'm gonna give you some time to try and solve this. You can either like make a list like this one. You can make a diagram, or if you have another way you think you can count those up, but see what you come up with. If she removes the restriction, she's going to wear any combination of the sneakers, the shirts, and the shorts. She's only going to wear one pair of sneakers, one shirt, and one pair of shorts. How many options does she have? You guys can work together if you want. Just the one of the Oh, you didn't like this one? How they did it? I think I'm very good. Hey, if you want to put your answers in the chat, you can. It helps me to know kind of as people are getting finished. Okay, I've gotten some answers in the chat. This is how I started the problem. Actually, let me just put this so far. I like to be efficient, so I didn't write out all the words. I just put W for white, B for blue, and R for red. So I said, okay, we can pair the white sneakers with each of the 3 shirts. And then once I pick sneakers and shirt, I can pick 3 more different varieties of shorts. And that happens for each of the shirts that I choose. I still have 3 choices for the shorts. Science and social studies, language arts. Yeah. Okay. Just a minute. Okay, so if you take a look, you can count just with the white sneakers. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 choices. And you could really stop there because I'm going to have the same amount of choices with the blue sneakers. So you could have started here and go, oh, I can see the answer. And the answer is 18. Or you can actually write out all of the answers. And you would do the same thing with your blue sneakers. You'd pair it with each of your shirts. And then each of those shirts could be paired with 3 different pairs of shorts. And so when you get them all put together, you have 9 plus 9 more, or you have a total of 18. Are there thoughts or questions about that? Okay, give me just a minute. Okay, so we've got 9 plus 9, or we've got 18 choices. All right, so if you take a look at the next page, and let's take a look at like numbers 1 and 2. So for 1, a television network is planning its Thursday night lineup. It has 2 sitcoms, 1 drama, and 1 reality show planned for Thursdays. And how many different orders could the programs be shown? And so one way, again, if you want to be efficient, you could say, I have sitcom 1, I have sitcom 2, I have a drama, and I have a reality. Okay. So they're asking how many ways could the programs be shown, in what order? And then number 2 is a little bit different. It says a car can seat 2 people in the back and 2 in the front. A mother and her 2 children get in the car, and how many different ways could the family be seated if the mother always has to be the driver and either child can sit up front? So this time we have the mother, and we have child 1, and we have child 2. Children can't drive. And once the mother is in place in the driver's seat, the children can sit in the back together. They could sit one in front, one in back, the other in front and back. And so see what you can do with number 1 and number 2. And let's assume for the car problem that if the children are sitting in the back, you can have them 1 and 2, or you can have them 2 and 1, and that those are different. Because remember, kids fight over which side of the car they sit in. When my kids were growing up, we had in the back 1 window that was broken and wouldn't go down. And so we had discussions about who got to sit on the opening window side. So child 1 on the left and 2 on the right is different than vice versa. So see what you can do. You can make a list, you can make a diagram, you could draw the car and all the kids in it. But see what you can do with number 1 and number 2. As you finish, you can put your answers in the chat if you'd like some feedback. Mom has to stay in the driver's seat. Okay, I'm hearing from some of you that you're finished. So, can anyone tell me the absolutely shortcut, didn't have to do any work answer for number 1? There was I didn't have to do anything at all answer for number 1. Anybody get the trick? Number 1 is the same problem as the first example. Anytime you are trying to arrange 4 things in a line and how many ways you can line them up, it doesn't matter if it's children or sitcoms or books or balls or whatever. If you have 4 things and they can be put in any order and you're trying to count how many, then there's always 24 ways. Okay, so you could do this problem just like the example if you wanted, only substituting instead of A, B, C, D, you might have used, like I said, S1, S2, D, and R. You could have made a list just like we did in example 1 to get 24. Or you could have made this kind of tree diagram as well. If I start with sitcom 1 and what are my other choices? Okay. Or you could have said 4 kids in a line and 4 TV shows in a line is all the same. Anytime you have 4 things that can all be used in a line, there's exactly 24 ways. Okay. And if you didn't see the shortcut, that's probably better because then you got some practice on arranging those 4 things in different ways. Okay, for number 2, this is what made sense to my brain, and it may look different than what you drew to figure out how many there were. I said, I'm going to have the front of the car and I'm going to have the back of the car. And I'm going to place my mother and children. Okay, and so this is 1 car and this is 2 cars and so on. Okay, and I put F because all these are, this is the front of the car, this top row, this is all the front of the car, and then the bottom row is the back of the car. Okay, you may have drawn it out differently, or you may have figured it out a different way, but this is what made sense to my head. So I always put the mom, of course, in the driver's seat in each of these cars. Okay, so I said child 1 gets to ride shotgun. So if child 1 is in shotgun, then child 2 has 2 places to sit. He can sit on the right side and look out the window, or he can sit on the left side and look out the window. And so then I did the same thing, but I put the second child up in front. And again, there's the same 2 choices. The first child now can sit on the right side of the car, or the child can sit on the left side of the car. And then I ran out of space. So I came down here and I said, okay, mother's still driving and now nobody's sitting in the front seat of the car. We can have child 2, child 1, or we can reverse them, child 1 and child 2. And so I came up with a total of 6 possibilities. And I got some answers in the chat of 6. Anyone want to share another way they organized themselves to figure out 6? Okay, this is what made sense to my brain, but that may not be the diagram that made sense to your brain. So if you wrote it out differently, but you figured out the answer, great. Okay. All right. So ultimately, our goal, though, is that we don't want to have to write out diagrams for every kind of this problem, because if I tell you that I have a, let's say I have a locker combination. Well, this is a better example. You want to play the lottery and there are 6, you pick 6 numbers, and how many possible options are there? If you can put a different, you have to pick a number for each of 6 places. How many total possibilities are there? You would spend all day in a ream of paper trying to write out all the possibilities. And so what we want to do is find a mathematical solution so that we don't always have to draw diagrams. Sometimes diagrams work, make sense, and might even be the most efficient way to solve the problem. But in general, as the numbers get bigger, it gets more challenging. So I'm going to leave page 59. These are kind of like puzzles in some sense. If this is something you want to continue working on, you've got 4 more problems. Remember, you have the answers. Your answers are in the back of this packet as well. And so if you want to challenge yourself to complete these problems, I would encourage you to do so. But we're going to move on to page 3. And a vocabulary word is permutation. And I don't know how important it is exactly that you know the word permutation, but the concept is really important. And we're gonna learn about permutations in this lesson, and then Thursday we're gonna learn about what are called combinations, and knowing the difference between them, even if you don't remember which word goes with which, is really important. And so it says in the last lesson, you counted the possible ways that 4 children could line up for a photograph. A way was considered different if the children were in a different order. When order matters, you are counting the number of permutations. And so the key to this concept that we're doing is we're solving problems where order matters. For example, if I want to find out how many ways 3 runners can come in first, second, and third place, order matters because first place is different than second place, and so on. If I'm just counting, I want to know how many ways I can put 3 people on a committee where they're just people on a committee, the order doesn't matter. That's a different kind of problem. That's the combinations that we're going to do tomorrow. But we're going to work on things where if they're in one order and then we change the order, that's considered something different. Just like the children in the car, when they swapped places in the back seat, that was different. And we counted that as a different answer than them sitting reversed. Okay. And it says in real life, the word combination is often used when it's really a permutation. And if you think about a combination lock, if you have a lock on a locker or on a storage unit or whatever, when you put the numbers in for the lock, the order you put the numbers in matters. If my 3 numbers are 5, 18, and 22, I can't put them into the combination as 18, 22, 5. I have to put them in the proper order. And so what the kind of joke they're making is, we call this a combination lock, but really it would be called a permutation lock because the order we put those numbers in does matter. If you think about your PIN number for like a bank account or a computer login, your PIN number, typically 4 numbers, sometimes 6, or for your phone, if you put those in the wrong order, the phone or the computer rejects it. And so your PIN number would be an example of a permutation. The order of the numbers matters. And so we're going to look at combinations later. We're going to start with permutations. And so this is the same problem as the ordering the children in the photograph or putting the TV shows in order. But now we're going to be able to do problems where there's bigger numbers because we have a shortcut math way to do it. So example 1 says, how many different ways can a student arrange 5 different books on a shelf? Now, if it was 4 books, we already know the answer. Remember, it's 24. But now we have 5, and we've got a lot more. If we were to diagram it out, that diagram is going to get bigger and bigger. Every time we add 1 book, it adds a lot. And so the way we think about this is when I place my first book on the shelf, there's 5 choices. There's 5 books I could put in the first slot. Once I've placed my first book, how many books are left for the second slot that I can choose from? There's only 4 books left for the second slot. And then once I've chosen the first 2 books, in the next slot, I only have 3 books left that could go in that slot. And so on until when I get to the last place, if I've already placed 4 of the books, there's only 1 book left. Okay. So the shortcut, super easy math problem, if you were to get this on the GED, is to find the answer. You simply take 5 times 4 times 3 times 2 times 1. And that gives you the number of possible ways that you can place 5 books. And you can see they've multiplied it out for you. 5 times 4 times 3 times 2 times 1 is 120. So when we went from 4 kids, putting them in a row and having 24 options, when we just add 1 more kid or 1 more book and we go to 5, the number of possibilities jumps from 24 to 120. And that's why you don't want to have to diagram out the whole thing. Or if you forget the rule, maybe you can start the diagram and then get the rule back in your head to calculate it out and see a pattern. But that is simply all you do. If the order matters, you take the biggest number. We have 5 books for the first choice, 4 books, 3 books, 2 books, 1 books. All the books are placed. We multiply all those numbers together and we get the answer. Okay. So nice thing is, if you were to get a problem like this on the GED, we don't want to miss these because these aren't real hard if we know the shortcuts. Okay. So example 1 used all the books. Okay. Example 2 is same idea, except we're not going to use all the people. Okay. So this is an example where we have 15 runners. And I want to know how many different finishes can there be for first, second, and third. So instead of placing all 15 books or all 15 runners, I'm only placing 3 because those are the guys that get the medals or the trophies or whatever. Okay. So I want to know how many different ways can 15 runners finish in the top 3. And so you can see they've drawn some little runners for us. There are 15 ways, 15 runners that could get first place. And then once we've identified a runner for our first place, there are only 14 runners who could cross the line in second place. And once the second place runner has crossed the line, there's only 13 runners left who could cross the line in third place. So in this problem, we're only going to multiply first, second, and third place because that's all we want to know. And so you multiply 15 times 14 times 13. And I assume their math is correct. 15 times 14 times 13. There are 2,730 ways that 15 runners could place first, second, and third. So we didn't go all the way, count down all the way to 1 because we weren't asking the question, how many ways can we order all 15 runners? We were just asking the question, how many ways can they finish in the top 3? Thoughts or questions about that? And the differences between these 2 problems? Okay, third kind of problem is like a problem like the lottery or like a combination lock or a permutation lock. And that is, for this particular example, it says a bike combination lock has 3 dials, each with 10 numbers. To open the lock, you turn the dials. A number can be used more than once. So how many permutations are possible? So in other words, how many different combinations, well, permutations, but what we call combinations you could put in the lock are there when you can reuse numbers? Okay. This problem looks a little bit different in that when I'm choosing my numbers, how many choices do I have for the first number in the sequence? I have 10 choices. Now, in the other problems, we would go, oh, 9 and 8. But think about this problem. For the second number, how many choices do I have? I still have 10 choices because I can reuse the numbers. In the runner's problem or the book problem, I can't reuse the book. Once it's placed, it's placed. If the runner runs across first, he's done. He doesn't run across second also. And in this problem, I can reuse the numbers. So I still have 10 choices for the second number, and I still have 10 choices for the third number. And so instead of being 10, 9, 8, if I can reuse the numbers, so there's still the same number of choices each time, now I'm multiplying 10 times 10 times 10. And there are 1,000 different permutations of 3 numbers if you have 10 choices for each number. So for example, if you were going to make a pin number with 4 numbers, okay, like if you think if your phone, if you unlock your phone with a pin number, I know some people use more than 4 numbers, but let's just start with 4. Okay. There are 10 choices for the first digit of your PIN number because we have 0 through 9, which is 10 digits. So you would have 10 choices for your first number, 10 for your second number, because in a PIN number you can repeat, 10 for your third, and 10 for your fourth. And so there would be 10,000 different choices. And that's why a PIN number with 4 digits is pretty darn secure. Because if you think about the likelihood of someone guessing your PIN number, there's 10,000 different iterations for your PIN number. Okay. And so it's not likely someone is going to guess it. Okay. I had an interesting situation. I applied for a Circle K card to get 10 cents off my gas every time. And I had to do a PIN, but the rule was, there's a 4-digit PIN, but the rule was the first number could not be 0, which is really bummed me out because I tend to use 0 for my first number of my PINs. And so I had to pick a different one. So let's see how many choices there are in a 4-digit PIN, but you can't use 0 for the first one. So how many choices do I have for digit 1? I only have 9 choices because 0 is not a part of it. How many choices do I have for the second number? The second, third, and fourth can be any of the 10 numbers.
Oh, okay.
So we would have 10 choices for number 2. The rule for 0, for some reason, very strange, the first digit could not be 0, but the other numbers could be anything I wanted. And so there would be 9,000 choices for that particular PIN because they eliminated only 1 digit in the first place, and that took away 1,000 possibilities. Okay. So these aren't hard, but you do have to think about what the parameters they give you mean for the numbers as you place them in the spaces. And a lot of people tend to either label them like this, number 1, 2, or 3, or they draw lines for, like, if they know they're going to have 4 things, and then they fill in the numbers and then they multiply them. So I would encourage you to get a system that kind of works for you for calculating these. Okay, so let's take a look at number 1. It says Jasmine has 8 songs in a playlist. The playlist is set to play songs randomly. If she listens to 3 songs, how many different orders are possible if a song may not be repeated? And that's a key thing, information. So I have 8 songs, and she's going to listen to 3 songs, but no repeats. So one way to do this is to say I've got 3 songs, so I'm going to draw 3 lines. Or you could do number 1, number 2, number 3, like up here. And we have to answer the question for song number 1, how many choices are there?
3.
There's more than 3, because how many total songs does she have? She's got 8 songs that could be in that position. Okay. So all 8 songs are possibilities for the first play. Once she's had the first song and we move to the second song, how many choices are there for the second song? There's only 7 because there's no repeats. If we could repeat a song, then there would still be 8 choices, but there's not because we cannot repeat. And then for the third song, we've already had 2 songs played, so those 2 songs cannot be played again. And so now I have only 6 songs that are left for the third position. And I multiply those 3 numbers. And there's my calculator. So 8 times 7 times 6 is 336. So you can see how the numbers can get big pretty quick, and a calculator will be your friend on these problems. But let's take time, see what you can do in terms of 2 through 4, or 2, 3, and 4, with the time that we have left. And before class is over, we'll go over these and see how you're doing. Anything from A to Z here. Let's see this letter come up. What are the choices for this letter? All the other speeds are Z, right? Which is not many. This two is just coming in. Mike, you can put your answers in the chat and let me know how you're going, how you're doing. Right, if you finish those four before we start discussing them, you can feel free to move on because those problems are going to be ones that I'm going to leave for you. Or you can go back and work on some review from the previous packet while you're waiting for the rest of us. Yeah, yeah. I didn't do it. I went back to these questions. What I mean, you. What is it? She said. Yeah, I'm starting to get some answers in the chat, so give me just a couple more minutes and then we'll talk about these three. Okay, let's take a look 2, 3, and 4 and see how you're doing. For number 2, we've got to make sure we get the important facts out of the problem. So the code has 2 letters followed by a single digit number. And the other important fact is the letters have to be different. Okay, that impacts how many choices we have for letters. And so the first thing I would do to solve this problem is write 3 lines because my code has 3 elements. And on top, or you can put it on bottom, I put LLN, stands for I need 2 letters and then a number. And then I'm filling in the number of choices that I have for each of those slots. For slot number 1, it's a letter. It can be any letter A to Z, and there gives us the hint that there are 26 letters in the alphabet. So there's 26 choices or possibilities A through Z for my first letter. Once the first letter has been chosen, there's not 26 left for the second letter because it says the letters must be different. If the letters didn't have to be different, you could put 26 in here again. But since they cannot be the same, once the first letter is chosen, like let's say A is the first letter, there's only B through Z left for the second letter. So there's 25 choices left for the second letter. And then for the number, we don't have 10 numbers this time because they didn't include 0. So we have 1 through 9. There's only 9 numbers. And then we take those 3 things and we multiply them together. So we take 26 times 25 times 9. And there are 5,850 combinations or different codes that could be assigned to customers. Any thoughts or questions about that? I really think it's helpful if you'll draw some lines or some labels that you're looking for to fill 3 slots to start with. Okay. And so I did that for 3 and for number 4. For number 3, she's got to choose 4 books out of 12. And obviously she's not going to read the same book twice. Or the English teacher would get probably people who just read the same book 4 times. So they've got to be different. And how many different ways can she complete the assignment to read 4 books out of 12? And so I made 4 lines that stand for book 1, book 2, book 3, and book 4. Okay. She's going to choose her first book, and there are 12 books to choose from. So let's say she chooses The Scarlet Letter for book 1. That's what she's chosen. So now when she goes to read her second book, there are not 12 books left because she cannot reread that book. There's only 11 left.
Hopefully she chooses a happier story for the second book to kind of.
What would you like for her to choose for the second book, Julie?
Like Through the Looking Glass or something?
Okay, she chooses Through the Looking Glass for her second book. And so on. Each time she reads one book, there's 1 less to choose from. And by the time she gets to her 4th book, there's 9 books left that she can choose. And we are going to multiply all these together. And so 12 times 11 times 10 times 9 is 11,880. Whoops. 11,880 ways she could order those books. To read. Okay. Thoughts or questions? All right. So number 4, there was again a very easy way to get this with absolutely no math. Or you could do the math. This problem is the exact same problem as example 1. Because remember, it doesn't matter if it's 5 friends or 5 songs or 5 books or 5 whatevers. If you're putting 5 things in order and they have, every time you move somebody, it's a different order, it's the same problem. Okay. But if you didn't notice that, that's okay. Again, good practice. And so we have 5 friends that could stand in the first position. And once we've decided who's going to stand in the first position, there's only 4 friends left to stand in the second position, and 3 and 2. And by the time we've placed 4 people, there's only 1 guy left or 1 gal left to go in the last spot. Okay. So the times, we've ended up multiplying all these together. The times that you're going to count all the way down to 1 is when you have a group and you're going to use all of the group, because all of them are going to stand in the line. That's how you know when you're going to end up using all the numbers, like from 5 all the way down to 1 or 7 all the way down to 1, is when we're using everybody in the group is participating. And so it's going to be the same answer as example 1, which is 120. Okay. All right. I am going to leave the bottom 5 questions for you. If you'll notice, I wrote in my hand page 32. When you look back in the answers, you're looking for the answers that go with page 32. I put together 2 different pages. This one up here is page 61 from one resource. And so that'll be in the answers labeled for page 61. And these answers will be labeled for page 32 and the answers in the back. So these actually, I think, can be kind of fun and not real hard. And definitely, if we get a question like this on the GED, we want to get it right, because it doesn't take a lot of effort to do these problems. In the last few minutes, I just want to kind of just go over what our schedule's going to look like. We get Canvas drug over. Julie did a really nice job of putting our schedule on the Canvas page. So this is Canvas. And so our classes, fall 2 classes, are going to go for the next 3 weeks till December 14th. And then the college is still open the Monday, Tuesday, Wednesday of the following week. And so there'll be no classes, but we will be available. Different teachers will be available during those days if you want to do progress, if you need to do progress testing, or if you want to take a GED ready, or you just want to work one-on-one with a teacher. You could come into campuses to do that, or we can do that by Zoom. So there'll be 3 days that we'd be available to you. The college is closed from December 21st through January 1st. Nobody will be working during that time, but that's an amazing time to take some of these packets that you haven't finished, all the problems, and go through them. I probably will work something up that you can work on your own during that time. It'd be a great time to talk about, before that break, to talk about getting voucher codes to do GED ready tests. Or if you've gotten some good GED ready tests, that'd be a good time to actually take some. Well, actually, Julie, will the NAU testing center be open during then? Do you know?
I am not 100% sure. I would suppose that they probably would be closed.
Okay.
During that December 21st time span, but I would have to check on that. Or if any of you guys want to check.
So, but during that December 21 to January 1 would be a great time to work on problems or packets that you haven't finished, all the problems, or for other classes, or to take GED ready tests. You can take.
And you might be able to schedule the online style GED exams, which are a lot more cumbersome during that time, but probably not in person, at least during that December 21st time.
And then the college will open January 12th, but there's like 2 weeks between when the college opens and when classes actually start. And so again, teachers will be working that January 2nd through 12th, but there will not be classes. So basically, classes will be stopped for about a month. And 2 weeks of those, the college will be closed. 2 weeks of those will be open and available to you to for coaching. I would assume NAU would be back open and the testing center would be open. So begin thinking about how you want to plan out the coming 2 months, basically. And then our classes will resume on a Tuesday because Martin Luther King Day is January 15th. And then we'll have our spring 1 quarter. In math, we're going to be working on algebra, and a heavy percentage of the math test involves algebra. And so if you are like, I know I'm weak in algebra, or I didn't have much algebra at all, that would be a great time to attend. So if you have thoughts or questions, I'll stay on for a few more minutes, but that's kind of the game plan moving forward. Have a great day.
Yes. Good birthday. Take care.
We back at one?
Melissa's class is at 1 science. Yeah.
We back at one. I feel a lot better than you.
That's what they care. That.
Put the log out, so I just go to X, right?
Yeah, just close that, and then when you get to the desktop. Yeah, so go ahead and close that out, right?
All right. Yeah.
Oh, yeah, and then just it'll close everything. And then on the little log on. Yeah, right there. Double click.
Okay.
There. That's nice.
All right. See you guys at one.
Sounds good. Yeah, it doesn't seem as cold today either outside, I feel, than yesterday.
Thank you.
Take care, Eddie. I think. Yeah.